Hello, and welcome back to Shiksha DaCosta. Today we're going to look at the different features of quadratic relations. In this lesson, you're going to learn to check if a graph or a table of values actually represents a quadratic relation or something else. And you're going to be able to talk about all of the key features of that relation. To start off, I'm going to ask you to choose three different numbers for a, b, and c and insert them into the equation y equals ax squared plus bx plus c. Now I did say numbers, so you don't have to stick to just whole positive numbers, the naturals. You can choose integers, so you can go negative for any of them. You can even pick a rational number if you prefer to introduce a decimal. And once you're done that, I want you to fill out the table here using the equation that you have created. So pause the video here and see how long it takes you to go ahead and do that. Well, for my equation, I said, okay, for A, let me make it a negative number like -2. For B, let me make it a nice whole number, positive like 4. And I might go for a decimal for C, so I chose 2.5. And that would make my equation y equals -2 times x squared plus 4 times x plus 2.5, exactly the way you see here. And to fill out my table of values, well, I have a value for x here. So to find the y value, I'm going to take x, and I'm going to replace x wherever I see it in this equation, and then I'm going to evaluate all of this, and it's going to tell me what y is. Just like this. So you can see here I've got y equals -2 times x squared, x is -4, plus 4 times x, again the same value, -4, plus 2.5, and that's my equation right there. -4 squared is 16. -4 times 4 is -16. And then -2 times 16 is -32. Minus 16 plus 2.5 gives me -45.5. And I can keep going with all of these rows, just changing this from -4 to -3 to -2 to -1, 0, 1, 2, 3, and finally 4. So if you're able to do that, then you are, very successful at being able to create a table of values from its equation. And the table of values you've created, the relation you've created over here, is by definition going to be quadratic because our equation had an x squared term in it. So that is definitely going to be a quadratic relationship. Now I'm going to ask you to sketch a graph of your relation using your table of values, and through your points, I want you to try to draw a curve of best fit. Once you're done that, look for the first differences from your table and see what you notice. Pause the video here and take as long as you need to do that. Well, hopefully you recognize, okay, let's take this point right here and let's plot it at -4 as our x value, and just going down to -45.5 would be somewhere around here, right? It looks like I'm going here by tens, so 45.5 would be just a notch under the halfway point between -40 and -50. Then keep going, -3 and -27.5 would be like right over there. -2 and -13.5 would be maybe somewhere over there. And just like that, I'm going to plot all of the points from my table of values on my Cartesian coordinate plane. Notice when I plotted my axes, I left the y-axis with plenty of room because I knew I needed to go all the way down to past -45. But for my x-axis, I just went from just a little bit before -4 to just a little bit after +4. And now that I've got my points plotted out, let's sketch a curve of best fit. And that might look something like a parabola. Of course, this is something that I expected because I know that any quadratic relation produces a graph that looks like this curve that we call a parabola. Let's move on to finding the first differences. Now, if you got stuck at this point, no problem. To find the first differences of a table of values, let me help you out here. The definition of first differences basically means what is the difference, or when we subtract these two, remember the difference is the answer to a subtraction question. So when I subtract these two, what number do I have to add to -45.5 to get to -27.5? To find that out, I just need to subtract the two of them, so -27.5 minus negative 45.5 will give me the first difference, which is 18. So to get from here to here, all I have to do is add 18. What do I have to add to get from here to here? Well, very similarly, I can subtract these two, and that would give me 14. So from negative 27.5 plus 14 gets me negative 13.5. Plus 10 gets me negative 3.5. Plus 6 gets me 2.5. Plus 2 gives me 4.5. But now notice the points have started to decrease in their y values. Now I'm actually subtracting 2. And then to get from 2.5 to negative 3.5, I actually have to subtract 6. And then I have to subtract 10 to get to negative 13.5. So hopefully you were able to do something like this. And if not, pause the video here and go ahead and complete all of your first differences. And then think about this question. What do you notice? Well, hopefully you recognize that, hey, all of there seems to be a pattern here. They all seem to be going down by the same number. The first differences seem to be decreasing by 4. Well, at least in my my example. And if you look at your example, maybe you might notice something very similar. Maybe they don't go down by 4. Maybe they actually go up. But you should notice that all of these numbers right here, which we called the second differences, are actually all the same. And isn't that interesting? So if you know a lot about linear relations, you know that one way you can identify linear relations is if the first differences are constant. Well, something very similar applies to quadratic relations. They have constant second differences. And as we saw in this investigation, no matter what values you chose for A, B, and C, once you plug those into this equation, once you make an equation that is ax squared plus bx plus c, the graph of that will always end up being parabolic. The only case where it wouldn't be is if the a value was 0. So if this was 0, then 0 times x squared would just be 0, and you'd just be left with this portion right here. And if you notice, that is actually a linear relation. Mx plus b, well, m and b they could be any letter, so bx plus c basically means the same thing. Now, parabolas, if we're looking at the graph here, a parabola has a very distinct shape. And one of the most important features about a quadratic relation or about a parabola is it has a tip right here. That is where the maximum y value or the minimum y value is achieved. That tip has a very special name called the vertex. Just like the vertex is the corner of a shape, the vertex of a parabola is the very tip of it. And if you notice something else about the parabola, is it is actually sort of like a mirror image on the left and the right side. It has a property called symmetry. It's symmetrical on either side of the vertex. And this imaginary line that would sort of be the mirror on the left that reflects the left and right side upon each other, that line is called the axis of symmetry. Axis is another way to say the word line. So this is a line that creates symmetry across our quadratic relation. And every vertical line has a very similar structure to its equation. It's always x equals some number. And in this case, because this line goes through the vertex, remember the vertex has an x-coordinate and a y-coordinate, and because the axis of symmetry goes through the x-coordinate of the vertex, this number right here will always be the same as the x-coordinate of the vertex. So this will always be x equals, the axis of symmetry will always be x equals, and whatever this number is always going to be the same as the x-coordinate of the vertex. Without a graph, are you going to be able to determine if these relations are linear, or if they're quadratic, or if they're neither? Pause the video here and take as long as you need to see if you can figure out which of these is which. Well, if we were to look at the first one over here, hopefully you were able to come to the same conclusion that I did, that a quadratic, if I was just looking at a table of values, the way I would figure out if it's quadratic is if it had constant second differences. And so if I subtract the y values here, I can see, okay, they're actually going down by negative 0.4. Oh, and then they're actually going down by negative 0.4 again and again. And oh my gosh, if I keep doing this, I recognize that actually the first differences are constant. And that would make this not a quadratic relation, but it would make it a linear relation. Going to the next one, this one is a little bit harder because there are fractions all over the place here. And if I were to subtract these two, the best answer I can get as a fraction, the first difference, is 3 256ths. And then to get from 1/64th to 1/16th, you have to add 3 64ths. To get from 1/16th to 1/4, you have to add 3 16ths. Then to get from 1/4 to 1, you have to add 3/4, and then you have to add 3 to get to 4, 12 to get to 16, 48 to get to 64, and 192 to get to 256. So the first differences are not constant. That means this is definitely not going to be a linear relation. If I were to check out the second differences, it gets even kind of almost harder here. So we have to add 9 256ths and then 9 64ths to get from 3 64ths to 3 16ths. And you can see already these are not the same number. And if we were to continue this pattern, we would see that there might be a pattern for the second differences, but they're not constant. They are not exactly the same number. And because this relation does not have constant first differences or constant second differences, this is not going to be linear, and it's not going to be quadratic either. This is neither. Finally, looking at our last relation here, the first differences seem to be, it's decreasing for now. Oh, and then it just starts to increase. Oh, whoops, sorry, no, it at the end here. Oh, wait, sorry, I got that backwards. It's actually increasing first, and then just here at the end, it finally starts to decrease. And if I were to look at these, I can say, okay, the first differences are definitely not constant, so it's not going to be linear. But is it going to be quadratic? If I look at the second differences, yeah, actually, these all do seem to be the exact same. So this would be a quadratic relation. What are the coordinates of the vertex of this parabola, and what is the equation of the axis of symmetry? Pause the video here and see if you can figure out the answers to these two questions, and I think you'll find them quite short. Well, the vertex, as explained, is just the tip of the parabola. So it looks like it's right over here. Now, if I were to put a point there, the coordinates of that point on the x-axis would be 3, and on the y-axis, this point would be, looks like, at 0. So the coordinates are simply 3 and 0. As for the equation of the axis of symmetry, now that we have the vertex, it's so easy to find. We know that it is a vertical line, and vertical lines always have the equation x equals some number. And so that vertical line right here, the axis of symmetry, will just be x equals 3. Because we know that that number here is always going to be the same as the x coordinate of the vertex. If you like this video, please like, rate, subscribe, and join our mailing list. And you can find this lesson as well as practice questions, solutions, handouts, and more on our storefront. Thanks and have a great day.